Hi, and welcome to this playlist on Hi, and welcome to the series on Intro to Theory of Computation. I'm your host, Ryan Doherty, and what this video is about is to get you familiarized with what theory of computation is and why we actually care about it. So what do these terms actually mean? So introduction, obviously. Theory just means study of. So what we're going to be studying here is computation. So what is computation? The central question that we're going to try to answer is, what can computers do? And are there any fundamental limits that they can do? So when we develop a program, when we write a program to solve a problem, clearly we can solve that problem, but the question is, can we actually solve every problem? So I'll motivate this with an example. So I had a computer in grad school. I'll try to draw it, even though I am absolutely terrible at drawing. Failed art, obviously. And I have my computer sitting right here. Let's see, it draws like something like this. And I wrote a computer program in here. And what I did was I tried to solve a particular research problem that I was interested in. And what I did was I wrote my program and I just set the machine running. So think about how long that this program actually ran. Try to guess how long that it actually ran into the comments below before I reveal how long it took. Did it take like a minute? Did it take an hour? Did it take a day? How long do you think that it ran? So the answer is that it ran for 6 consecutive weeks. So this computer right here was just churning on my desktop for 6 consecutive weeks without stopping, and it eventually produced the result that I was interested in, but it ran for that long. So the question to you is, let's say that you are some person right here and you're seeing that this program is running right now, and what you want to do is determine whether or not it will stop. So maybe what you can do, maybe we can call this file, let's call it file.py. It wasn't in Python, but let's just go with me here. So this file is file.py, and what you do, and let's say that you want to make lots of money, what you can do is write some different program. So maybe that this is some awesome program.py, and what it does, you hope, is you would take this file in. So this file comes into your awesome thing. So this is coming as input, and the output of this is going to tell us whether or not that program is going to stop. So maybe you could say that the output is going to be a 1 if the input stops, and 0 otherwise. Or you can associate that as true and false. It doesn't really matter here. But the meaning of this is that there's an algorithm where you can feed in this program, and the output of it is going to tell whether that program's going to stop. Because if you look at this program running, it's not intuitively obvious whether or not this program is going to stop as you're watching it run. You can maybe look at it and go, oh yeah, you have this infinite loop going, and so therefore your program runs forever. Or maybe you have, because it's Python, maybe you can say, well, this loop iterates at most 100 times and you're on loop iteration 99 and the last one's not going to take forever. So maybe it will actually stop. It just might take a really, really long time. It turned out in this case that the program never actually did stop, but it just got to the point where I said I got the result that I wanted. So you may think, okay, I'm going to sell this to Google or Facebook or really any research lab in the entire world. And you can say, well, I'm going to sell my product closed source, and I'm going to make lots of money because they can formulate the research problem in terms of a program. And instead of spending millions of dollars Instead of spending millions of dollars waiting for this program to actually stop in terms of computational resources, this awesome utility is going to be able to determine all of that for us much faster. And the problem with that is what we're going to see in the class is that this is impossible. It's literally impossible to write an algorithm that solves this problem. Which is kind of sad if you think about it. You can't tell whether a program even stops, but it's an important question, and it's important why we do this in a theoretical way. Why is it important? So the question here is asking whether an arbitrary program fed as input, we can determine whether or not it will stop or not. That is impossible. However, if you're looking at a specific program, like my particular research program, that either stops or it doesn't. So it is possible to determine for a singular program whether or not it will stop. However, when we deal with it in the general case for every possible program, then it becomes impossible. So the question is, how do we make this precise and formal? That's what the theory part is for. How do we represent these machines in a formal way so that no matter who you are, no matter what your opinions are, we can prove it without any uncertainty? And that's what the class is about. But there's actually a lot more to the class than just that. It's not just this. So here I've written a program in Python. You can write it in C or Java, but the same analogies will hold. So it's not really any different. It turns out that we can do a lot more than this. If we did just this, it would be very important, obviously, but we can say a lot more than this. So let's say that we have a program right here, and let's just call it file.py. And let's say that it accesses a lot of data. So let's say that I access 1 gigabyte of data. Let's say that it accesses 1 gigabyte of data. And it took those 6 consecutive weeks. It didn't actually take that much data, but it didn't take that much data, but let's just follow me. Well, let's say that I'm going to restrict this thing quite a bit. So maybe I'm going to restrict it. So I'm going to have a restricted version of it where I say, you can only get 10 megabytes of data. Maybe I want to run this program a little faster, and I'm just going to limit the amount of allocated RAM that it can use. So maybe that will run a little bit faster, potentially. And maybe I will get even a more restriction. Maybe I'll get a more restricted one. So I'll develop a different algorithm that uses less data. So let's say 10 kilobytes of data instead of 10 megabytes. That's actually really pushing it. But so we can see that there is a huge reduction in memory. And then the question that we would want to answer is, does a reduction in memory cause us to solve fewer problems? And that's a totally natural question. So if I restrict the amount of memory that you can access, are there some algorithms that you can't solve? And this is actually provably true. So let's say that I wanted to determine, just as an example, let's say that we wanted to determine if the input data is at least 2 gigabytes in size. Maybe it's coming in as a stream, it's streaming data, we're maybe streaming things from Twitter or something, and we want to know whether the thing's at least 2 gigabytes in size. Well, it's not super hard to deal with it here. It's getting a little harder here, and it's getting really, really hard right here. And if I eventually go far enough, maybe say 100 bytes of data, then this is actually really, really, really pushing it. It turns out that there's a fundamental limit to how far we can go down before we can't actually represent this data. So the question that we will try to answer in the class is there a fundamental limitation to how much data? Is there a fundamental limitation to how many problems that we can solve if we restrict the amount of memory that we can use? And it turns out that there's quite a bit. So this idea of is really, really pushing it is intuitive, but it's not actually formal. So how do we actually make this more formal? Well, what we can do is we can actually classify machines in terms of their capabilities. So we have the intuitive notion of computers as we know them today. And computers as we know them today could, in principle, allocate as much as they want. There are fundamental limitations physically, but in principle, they can access as much as they want. So they can do access unlimited memory. It just might take a really, really long time to actually access all that memory, but in principle, it can be done. But what we're going to do is we're going to try to restrict this. So maybe we would tell you, okay, you have a fixed amount of memory. Then what kinds of problems can you solve? Well, you can actually, with a really small amount of data, you can actually solve this particular problem, because 2 gigabytes is roughly, so let's actually calculate how big 2 gigabytes is. So that's actually 2 times 1024 to the 3rd power bytes. So if you actually calculate this, then you can actually store the amount of bytes that you see in a really tiny package. Because we write things usually in binary, you can actually store this number in a surprisingly small number of bytes. It's just that there's a fundamental limit in doing so. But the question is, well, what if we make inputs really, really large, maybe like 2 terabytes? Then that's going to start becoming a problem if we have a really, really small amount of data. Well, here, what we try to do is we tell you, you have a fixed amount of memory. No matter how big the input is, you have a fixed amount. So the different models that we consider in this class are a fixed amount of memory, where you're not allowed to allocate anything else other than the memory that you got, but also we're going to restrict how you access the input. So the input, in principle, you can access in any way that you want. So like if you have an array of something, you can access any particular element that you want. But one model that we will consider is we can only access the input in a forward fashion. So forward only input. And by that I mean you can only access the things in the input in a forward way. So you can access the first character, then the second character, but you can't go back. Okay. And then what we do, so this is the first one. The second one is we're going to have a fixed amount of memory also and a forward only input, but we're also going to allow ourselves a single stack of memory. So add a stack. So we're going to add a stack of memory. And this stack can grow as large as you want. So effectively, the first one, if we only have a fixed amount of memory, we, in principle, as we'll see, can't count things precisely. Whereas with the stack, we can somewhat count things precisely, because if I'm trying to match something against something else, then I put the first thing on the stack, and then the second thing I can match up with the things on the stack. And it could be a queue. It's not necessarily that important right here, but as long as we have some kind of data structure, then that will be really helpful. And then the third and final one, which turns out to be equivalent to real computers, is we add a tape instead of a stack. Okay, so instead of a stack, we're going to have a tape. And so that allows us to access things differently. And the key point of the class is to be able to think about different accesses to data will result in different powers of machines in terms of what you can do. So the class is all about what things can the first one do and what things can the first one not do. And we have to be able to prove those types of things. Then the second one obviously does at least as much. Then asking, are there things that the two machine can do that the one machine can't do? And it turns out that there are. And also asking, are there things that the two machine can't do? And there, in fact, are, and we got to prove those too. And then there are things that the three machine can do that the two can't do. And 3, for as far as we can tell, is the fundamental limit. 3 is equivalent to our notion of computers. So we can actually convert any program that we want into a machine that has a fixed amount of memory and has a tape amount of memory also. And the tape can grow just like the stack can. And it turns out that that's equivalent to computers also. And finally, if those are equivalent to computers, we would want to know whether there are things that the 3 machine can't do, that there are things that the 3 machine can't do, and it turns out that there are plenty of things. And I want to give you a quick and dirty proof that the vast majority, so I want to give a quick proof that the vast majority of problems are just not solvable even by the 3 machine, which are our notion of computers as we know them today. So if we think about it, let's think about a particular program. So I have a program right here, and it's got a bunch of code in it, maybe data, it doesn't really matter. Well, we can actually think of it as it's stored on the hard drive. It's just a bunch of zeros and ones. So on the hard drive, or solid state if you want, it's just a big long string of zeros and ones, something like that. Then we can actually interpret all of this as one big, really big binary number. So this is one big binary number. Oh, just a number is equivalent. So therefore, the number of possible programs that we could ever have is at most the number of integers. So the number of possible programs is at most the number of binary numbers. Because it very well could be that there is some binary number that doesn't encode a program at all. That's totally possible. And we're only considering valid programs, but it doesn't actually matter. It's just pieces of data. That's all that really matters. But even with programs. And obviously, each program can only solve one problem. So the number of solvable problems, what we want to do is compare this with the number of, we want to compare this with the number of possible programs. What we want to do is we want to compare this to the number of possible problems. So if the number of solvable problems is way smaller than the number of possible problems, then clearly there are many problems that don't have a solver for them. They don't have a program for them. So what we're going to show is that this is way, way, way less than the number of possible problems. And it's pretty easy to see this. And so why is that? Well, what we can do is we can phrase a problem in a certain way. So each problem, what is it? So it is taking some input and converting it into output. And so each one of these inputs can be any arbitrary input at all. So that can be, in principle, any binary string. So these are the set of binary strings. And it doesn't have to be binary, it could be unary or ternary. It doesn't really matter exactly what it is, but as long as we have an infinite number of things here, because there are infinitely many possible inputs. And for the same reason, in principle, there are infinitely many possible outputs. Remember, this is possible problems, not the ones that are realizable necessarily. So the output is a set of binary strings too. So here's the key point. The number of possible functions from this set to this set is an uncountable infinity. So the number of possible problems is an uncountable infinity. So I don't really like this term. Uncountable just means that there's no way to list anything. So for the solvable problems, I can tell you what the first one is, I can tell you what the second one is, I can tell you what the third one is, and the fourth one, fifth one, all the way up. Any one that you're interested in, I will eventually get to you. Whereas with here, this is not possible. So uncountable means that it's literally not possible to list all of the possible problems in any order to be and guarantee to hit every single one. It's literally impossible. And if you happen to know Cantor's diagonalization argument, that's exactly what this is. All right, so hopefully that was interesting. Leave thoughts about theory of computation down into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.